Hey guys, so welcome to your very first flipped classroom video. I know it's a new experience and it's almost a little intimidating, but I am going to walk you through this pretty slowly. We should be watching this video in class together, or at least I'm walking around hopefully helping you so that there are no questions or super huge confused faces. How we start these videos is I kind of give you a little spill in the beginning and then we get into it. The next slide is going to be all on objectives, so the things that I think you should know by the end of the video. And then as the slides progress, we talk about different concepts. Your goal to watch the video, the best thing to do is to listen and to really try and listen and gain everything that I'm saying in the videos. And so what I mean by that is I don't really want you to spend a whole bunch of time writing notes. And I'm going to talk about that in class. Like, I know I want your notes to be done by the time I talk about this in a lecture method, but I don't want you to spend the whole video writing the notes and then ignoring me as I'm talking. That's not the point of the videos. The video is really for you to get the information so you have a basic understanding or a basic framework. So when we actually talk about it in class, you know what I'm talking about and it's not just like a bunch of gibberish. This video is going to be a little bit longer than I usually make these because of the fact that this is an introduction video. So I'm going to walk things a little bit more slow. I do talk very fast. That's something that last year's group told me. So I am working on that. We all have our faults. If any time I am going too fast, I always recommend rewatching a portion of the video or just asking me in class. So just like write a portion in your notebook and say, I didn't understand this part. You were talking too fast. You were jabbering about so-and-so, whatever the case may be. The videos that I'm going to go are all the videos have information, and I will always link a reading to this information. So it's not going to be something that you won't have anything to fall back on. If you don't understand something and you want to do some reading from the text, I have the link sent with the video. With that being said, let's go ahead and get started. Just disclosure, I am sitting outside. So if you hear any cars go by, that is what's going on. All right, so like I said, the next slide is going to be the objective slide. And the objective slide, you do not need to write down. Do not write these things down. These are not things I want you to write down. These are things that I feel like you should be able to do or know by the end of the video. But it's not necessary to write them down. So the things you should know. Identify the goal of science. Describe how scientists study the natural world. Explain how and why scientists do experiments. Describe types of scientific investigations, and finally explain what a scientific theory is. Generally, these objectives will correlate with the slides, as in I'll go with the same order, but I switched things up just a little bit this year, so some of these objectives are going to be a little bit out of order. And you'll see what I mean. When you are in class, you will write notes and you'll be adding to the things that I have in the video. But the things I have in the video are very short. I try not to make these notes super long. It's just a way for you to get the idea, and then I mostly just talk about it. So again, in class, I am going to be adding notes, and I have a notebook with my own personal set of notes. You are always welcome to use that notebook to copy your own or copy something that you missed in class or in the video. Please do not, like I said at the beginning, do not spend all your time just writing the notes and really ignoring the content. It's your choice if you choose to do that, but I give a lot of information when I'm talking. And I know last year students didn't take full advantage of the videos, and so you could really see that reflection in their grade. So that's just my disclosure. Use that information however you will. All right, so let's go ahead and talk about science. That's why we're here, right? We're learning about science and most importantly, biology. So the goal of science and why we actually want to learn about science, why we do science, because believe it or not, I know it seems that you just have to take this class because you're graduating, you want to graduate high school, but there are other reasons to learn science. And one of those things is because you actually see and do science every single day. You're sitting here listening to this video, science. You are getting up to go get a drink from the water fountain, science. All of these things that happen in your everyday life all exist because of science. And so believe it or not, some people actually want to study that. So the goal of science is to understand the natural world. And I'm going to go ahead and underline that. That is a big important point. Big thing when I underline or highlight something or star something, I always recommend that you know that. Those are big points that I want to get across. So the goal of science is to understand the natural world. And in order to do this, there are four things that scientists assume. So 4 ways to understand the natural world. The first one, nature can be understood through systematic study. And I'm going to go into detail in all of these things in the next 2 slides. So right now, if you want to leave space in between all of these 4 assumptions, I would recommend that. Ideas can change. They change all the time. Scientific ideas are always improving, always getting better. What we did in medicine 50 years ago is not what we do in medicine today. Some things, yes, not everything. So there's always constant change, always constant improvement. Ideas can always change. Sound scientific ideas last forever. So I'm kind of contradicting myself right here. But what I'm saying is that there are some theories out there that hold on or that are so strong and so backed up by evidence that they will continue to be correct and withstand all tests thrown at them, even in the future as technology progresses. Science cannot provide answers to all questions. This is a big one that we hit on right away because I know in biology a lot of people have really conflicting questions and conflicting ideas. So we'll talk about all that. So here is where I told you I was going to expand on every single idea. Now there are a lot of words on this. I don't recommend writing it all right now. Write the basic ideas, and then when we talk in class, I am going to write notes on the board. I'm going to go through all of this. So don't waste your time writing all of this. Or if you want to, write it after the video or whatever the case may be. But don't waste your time while I'm talking writing notes because you're not really going to get as much out of it. Like I said, you choose and you know yourself better than I do. So however you want to learn. Anyways, nature can be understood. So nature is viewed as a single system. So it's like this one intricate, beautiful little system that actually works all together. And what controls this or what keeps this system regulated is these natural laws. The idea that laws will always hold true. So a law is concrete. Laws of nature are expressed as scientific laws. Scientific laws is a statement that describes what always happens under certain conditions. So a great example of this is the law of gravity. And if you know anything about gravity, you know that's what actually is keeping us on the ground. And this was actually discovered by Isaac Newton. The law of gravity means that an object will fall towards Earth because of this force pushing us down. And that force is known as gravity. So based on this law, every single thing that's dropped towards the earth will fall and it'll hit the ground because of gravity. A law. It always holds true. It's never going to change. There's nothing that can stop that from happening unless, well, obviously there are other forces that can stop that from happening. But the fact of the matter is that the law of gravity is concrete. Now keep the idea of a law in the back of your mind because we are going to compare that to theories in the next slide. And so it's really important that you can distinguish between a law and a theory. And there's a big factor that allows you to distinguish between the two. Scientific ideas can change is the next assumption that's made in order to establish the goal of science. And that idea is, never mind, I am recording. Anyways, I do make a lot of bloopers in here and it's just one of those things. You'll learn that I'm pretty quirky and awkward, and that's just what it is. Anyway, so scientific law ideas can change. Existing ideas are always challenged and can be replaced. So I just told you that we have scientific laws. Those are things that are concrete, but there are also these ideas, and these ideas can be changed and they can be replaced. Many times they're not really replaced. They're more like revised or amended, if you will. And what I mean by this is that these ideas are just, they're taken from an observation, and then that observation is tested and it's formulated, and then it continues to be added to. So revised or expanded, evolved, if you will. And the great example of this is Einstein's theory of relativity. You are not actually required to know what Einstein's theory of relativity is, But basically what Einstein was doing was he was explaining the laws of physics and how things are moving or in motion with and without gravity. And you don't have to know that, but the idea is that Einstein used previous ideas to help add to his own theory. Okay, so ideas can change, they can expand, they can evolve, but generally they're not replaced. So an idea, if it's a pretty solid idea, it's going to usually be pretty held up. Now going on to this same idea of scientific ideas. So yes, they can be changed, but generally, not changed, revised, but generally when that revision happens, that idea, that core central portion of the idea is still there. And that idea can generally withstand the test of time. So a great example, again, we can use Einstein's theory of relativity. That theory still holds its value in physics today, and physicists use that, but they continue to try to add to that same theory. So Einstein, that was like 75 years ago, 100 years ago, and here we are still adding to that same theory. Another great example, and you've probably heard of this from last year, atomic theory. So when you learned about the atom, right? Everything is made of atoms, and that theory has been strong and held concrete for about 2,000 years. When you get into chemistry, we talk about that in a little more detail, but it was presented 2,000 years ago, and 200 years ago, there was another guy that came in and kind of stole the show. But again, that's not something I expect you to know. But atomic theory, long time withstanding, and we continue to add to that same theory. And finally, the last point or the last assumption that's made in order to understand the natural order of science or the goal of science is that not every answer can actually be, not all questions, can be answered using science. So science is really important that evidence and logic and reasoning are all the only things that apply to a scientific idea. You can't just say the sky is purple and expect people to believe that because you believe that it is purple. Well, based off millions of observers, they all say it's blue. So we use evidence and logic and observations to answer questions. If there is no evidence, logic, or observations to answer these questions, then it's not held reliable in science. So it's a great thing. You should definitely know the definition of observation. It's anything that is detected either through human senses or instruments or measuring devices. So you have to have some kind of qualitative or quantitative information that will back up your observation or back up your own theory. Can't just throw something out there and expect people to believe it to be true. All right, I am talking quite a bit in this video. Like I said, this video is going to be a little bit longer than I generally try and make these. My goal is to always make these less than 15 minutes or right at 15 minutes because I feel like at that point you're just like, I'm done. I don't want to do this anymore. This is just tedious. All right, so let's compare and contrast. We just talked about laws and how those laws are always and forever true, and they always explain a phenomenon. Now we're going to talk about a theory and how that is different. We're going to compare that. Scientific theory is a broad explanation for events that is widely accepted as true. So a scientific theory is widely accepted. Okay, now here is the big difference. A scientific theory cannot be proven. It can't. There is no way to concretely prove that a scientific theory is true. Now, that's not to say that work hasn't been done to back it up, but the fact of the matter is there is nothing true, concrete that proves that this idea is law. So how this happens or how this goes about is generally people throw out a hypothesis. And a hypothesis is this idea or this testable idea, and it's tested over and over again by various people in different scenarios, and there's large amounts of evidence to back that theory up. A great example of this is Darwin's theory of evolution. Not everybody believes in the idea of evolution, but the fact of the matter is it's a strong theory that explains how man came to be or how humans came to be. We are ancestors of different primate species or different mammalian species. Whether or not you believe that's true, there is evidence to back that up. That's a theory. A theory cannot be proven. Laws are always true. They always explain a phenomenon no matter what. And there are plenty of laws you probably learned about in Science 1. Newton's laws, great laws to talk about the motion of objects. Law of gravity is like another one that I just talked about. All of these laws always hold true. Law of conservation of mass, law of conservation of matter, all of these things, true every time. Theories, not proven. That's not to say that they're not backed up, supported, but they cannot be proven. That's the big difference. So if you don't, I'm going to write it down. Laws are always true. Theories, my handwriting is beautiful, are not. I guess I should say are not always proven, but I don't have any more room on my paper because you don't see it, but there's a little bar there that really stops me from writing anymore. But yes, theories, not proven. Laws, always true. Here we go. And the final portion we're going to talk about, the next 2 slides, is what's known as the scientific method. Now, if you notice on my slide, I have a specific order of things. The scientific method is actually not a series of steps. It's actually a lot more messy. It's great visually to see it as a series of steps, but it is so messy because you could ask a question, form a hypothesis, and then ask another question, and then form a different hypothesis. So you continue to go backwards and forwards. So this is really not a chain reaction. It's more of just like a guideline. So scientific method is a series of steps followed in scientific investigations. No matter what, every scientific investigation is always going to start by making an observation. Okay, and I'm going to give you some examples in class, so I'm not going to spend a whole bunch of time talking about those examples. But scientific method always starts with making an observation. From there, it forms into asking a question. A lot of times you can see that asking a question may be the first thing instead of making an observation, and that's okay. Either way, it leads us to this idea that we can now make or form a hypothesis. And a hypothesis is a testable explanation for something. So it's something we can test to see if it holds value or not. We test that hypothesis by doing experiments, and then after those experiments, we draw conclusions, and then we communicate our results, whether there's support or not support for a hypothesis. So next portion here, experiments. An experiment is a special type of scientific investigation that is performed under controlled conditions. I will be adding quite a bit of notes to this slide, so make sure you leave room. Sorry, Jace is talking to me. Give me a second. All right, so you probably all heard, sorry, I was talking to Jace, and so now I don't really know where I left off in the last point, so I'm just going to kind of start over. So you all heard of scientific experiments? It's maybe like some crazy scientist is in a lab mixing all this stuff and explodes something. Either way, an experiment is a way to test hypotheses. And generally you do this under controlled conditions in a lab. Experiments done anywhere else really have a lot of other factors that you can't really control. So the best way to do this is always in a lab or a controlled environment. So maybe like instead of in the kitchen, you do an experiment in your room so you can control more of the factors than everybody else. Dependent variable, there are 2 different types of variables that come into play in experiments, dependent and independent. I'm going to talk about these in a lot of detail in class, so I'm not going to waste your time now. In fact, I wouldn't even write the notes for it. I would just know that there are 2 variables, dependent and independent. Dependent is affected. Independent affects the dependent variable. And anything that will affect the dependent variable always needs to be controlled. In class, I will show you what a dependent and independent variable looks like on a graph. I will show you examples of what these look like, and we will be practicing identifying those things. So basically the first week is all just trying to understand what you know and getting a basic understanding of what you know. Okay, so don't worry if you're feeling so overwhelmed and so scared. You probably heard that biology is pretty hard, and yeah, I have high expectations, but I'm not going to just leave you out there hanging. I will definitely be there for every step of the way. You determine what grade you want, so I will always be there, whatever you need. You just have to ask me for help or some way communicate that to me. All right, with that being said, Make sure you answer your questions on Edpuzzle. Make sure you have your notebook for class. We will talk about all this in class. See ya.